from a photographic plane. Here is the motion picture spectacle of all time. A million tons of water alive with deadly rays. Awe-inspiring in its significance for man, who learned how to control the atom, but must now learn to control himself. There is but one defense against the atom bomb, and that is distance. And distance will mean nothing without world peace. This is Crossroads.
Hello and welcome to this presentation on the nuclear physics of nuclear fission weapons, presented by me, Shelby Matoyer, from the Texas A&M University, Kingsville, a Texas Physics Consortium affiliated campus. For the topic overview, we'll look at nuclear fission, the nuclear chain reaction, critical mass, modulated neutron initiators, fission bomb design, as well as the superiority of the implosion-style nuclear weapon. First, let's take a look at the nuclear fission of uranium-235, where one neutron combines with the uranium-235 nucleus, combining to make an unstable 236 uranium, which quickly fissions into barium-144, krypton-89, and approximately 3 neutrons. Similarly, if we look at the fission of plutonium-239, we'll see that one neutron collides with the plutonium-239 nucleus, putting it into the 240 state, which then undergoes fission, creating xenon-134, zirconium-103, and again, approximately 3 neutrons. Here, if we look at the energy released by both the uranium fission as well as the plutonium fission, shown here in the nuclear equations above, we can see that the Q value is the negative difference in mass times the speed of light squared, which, for uranium-235, can be calculated to be 173 MeV, and for plutonium-239, its Q value can be calculated to 188 MeV. So, the nuclear chain reaction, when one neutron hits the uranium-235 or plutonium-239 nucleus, causing it to fission, and then the 3 neutrons created from its nuclear fission go to find other uranium or plutonium nuclei, causing them to fission, creating more neutrons, which cause more plutonium or uranium to also undergo fission. This takes us to critical mass. Critical mass is the minimum amount of fissionable material needed for a nuclear chain reaction to be self-sustaining. That is, at least one neutron from the fission of uranium or plutonium will have a probability of hitting another nucleus, causing it to fission as well, and the neutron created from that fission, again, finds another nucleus. So there is constantly a chain reaction, but at a slow rate. As the mass of the material increases, it reaches a point which is called supercritical, in which almost all of the neutrons cause fission. This leads to a cascade and an enormous amount of energy released all at once. Below critical mass is subcritical, in which almost all of the neutrons escape before causing fission. So, what is a modulated neutron initiator? Well, in the case of Fat Man, the bomb dropped on Nagasaki by the Americans during World War II, it was a beryllium-polonium urchin, its code name given to it during the development. Polonium is highly radioactive and decays via alpha emission, with 1 in 100,000 causing gamma emission of approximately 803 keV. The gamma emission from the polonium knocks free a neutron from the beryllium-9 nucleus as the two are crushed together under high pressure and temperature. This interaction releases a burst of neutrons. So, let's talk about the fission bomb, also known as the atomic bomb. Here, taking a look at two of the fission bomb designs, on the left, the gun type, where approximately 1% of the uranium undergoes fission. At one end of the gun barrel is a subcritical hollow uranium bullet, which, after the gunpowder is exploded, accelerates down the gun barrel to come into contact with the cylindrical target, another piece of subcritical uranium. After the two come together, they form a supercritical massive uranium, which then undergoes fission, causing the explosion. On the right, we have an implosion type design, where approximately 20% of the plutonium undergoes fission. Here, the plutonium core is surrounded by a spherical shell of high explosives. The explosives are detonated uniformly, compressing the plutonium core, as well as the modulated neutron initiator, or the urchin, causing the burst of neutrons, which then go into the plutonium core, causing it to undergo fission in a nuclear chain reaction, releasing a burst of energy. Now, the implosion style of weapon is far more efficient than the gun type. The efficiency of a nuclear weapon is measured by how much material is able to undergo fission or fusion before the weapon destroys itself. Due to the inefficiency of the gun type design, where approximately 1% of the fissionable material undergoes fission, all modern nuclear fission weapons are some variation of the implosion type design, as well as hydrogen bombs being of the implosion type design, with none of them being of a gun type assembly. The implosion type design fission weapon tends to be used with plutonium as a primary fission material. A uranium pusher or reflector pushes the free neutrons that would otherwise escape back into the path of the plutonium atoms. This increases the efficiency. Once enough of the plutonium has undergone fission, the neutron count and energy reaches critical as a result of the fission of the plutonium. The secondary fission of the uranium accounts for approximately 20% of the weapon's potential energy. If you take the effectiveness of a nuclear weapon to be measured by how much material is able to undergo fission or fusion before the weapon destroys itself, then the implosions type design is far more efficient than the gun type design. Due to the inefficiency of the gun type design, where approximately 1% of nuclear material is able to undergo fission, all modern nuclear fission weapons are some variation of the implosion type design, where approximately 20% of the available fissionable material is able to undergo nuclear fission. The implosion-type design fission weapon tends to be used with plutonium as the primary fission material. A uranium pusher or reflector pushes the free neutrons that would otherwise escape back into the path of the plutonium atoms. Once enough plutonium has undergone fission, the neutron count and energy reaches critical as a result of the fission of the plutonium, thus igniting a secondary fission in the uranium, which accounts for approximately 20% of the weapon's yield.
25 May proof-tested another delivery system, the Army's 280-millimeter gun. When this shot was added to the program, some additional effects tests were scheduled to observe results of the low burst height, approximately 520 feet above ground. Since no gun-type assembly had been detonated since the Hiroshima bomb, the weapons development scientists had on this shot their first opportunity to study the nucleonic behavior and fireball configuration of such a device. Yield 15 kilotons. Unlike the situation with an implosion weapon, the scientists were here able to observe fireball growth from a body of fissionable material whose exact shape and dimensions at the moment of detonation were known.
Let's now take a look at the energy yields of fission bombs. Assuming that 20% of the available fission material can undergo fission during the course of the implosion, if we take 6.2 kilograms of plutonium, then only 1.24 kilograms of plutonium will undergo fission. 1.4 grams of plutonium is approximately 3.1 times 10 to the 24th atoms. And each fission of plutonium, as we found earlier, releases about 188 MeV, leading to a total yield of 5.9 times 10 to the 6 MeV, or approximately 22 kilotons of TNT. The approximate yield of Fat Man, the bomb dropped on Nagasaki. Fission bombs have yield as low as 0.01 kilotons of TNT. These are known as tactical nuclear weapons, such as Davy Crockett. The 0.01 kilotons is the near minimum amount of energy that could be released from any nuclear weapon, with upper limits at 500 kilotons of TNT, which was the largest pure fission weapon ever tested, Ivy King.
Zero. In the 56 seconds it takes the bomb to fall, the men of Operation Ivy wait on Parry and Eniwetok Islands. Unlike the Mike phase of the operation, the King phase will be observed from land. The bomb is now at 8,500 feet, at 6,500 feet, at 4,500 feet, at 2,500 feet, approaching 1,500 feet. Watch the air overrun it.
To sum up, we've learned today the process of nuclear fission, about the nuclear chain reaction, what critical mass is, modulated neutron initiators, fission bomb design, which we know comes in two varieties, the gun type design, where two subcritical pieces of uranium are brought together in a rapid succession by high explosives to form a supercritical mass of uranium, thus causing the chain reaction. With the implosion-type design, we've seen that the plutonium is compressed in order to reach a supercritical state, which the modulated neutron initiator starts the nuclear chain reaction. We've also learned that the implosions-type design of nuclear fission weapons is far superior. Furthermore, the implosion-type design was used later on to invent an even more powerful nuclear weapon, which used nuclear fusion. Throughout the course of my study of nuclear weapons, I learned how terrifying these weapons truly are. The field of nuclear physics is one that is rich, and the discovery of the nuclear processes underpinning the nuclear bombs have enriched humanity and science. However, the use of nuclear weapons on civilian populations, as well as their use as a weapon of terror, should be condemned to its fullest. Every nuclear weapon should be destroyed, and they're something that should never be used again. These weapons are weapons of mass destruction and weapons of terror.
Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another.